Hello everyone. In the last lecture we have discussed that interconversion of Newman, Sahars and Fisher. Now I am starting the conceptual part of optical isomerism, right? So first important thing what we need to discuss is meaning of optical isomers. What is the meaning of optical isomers? The meaning of optical isomers is stereoisomers show different optical behavior towards polarized light. I am writing here stereoisomers show different optical behavior towards plane polarized light. So, two stereoisomers show different optical behavior towards a plane polarized light, they are optical isomers. For example, compound have suppose two stereoisomers, one is A, second is suppose B. One stereoisomer rotating the polarized light in clockwise direction, second stereoisomer rotating the polarized light in anti-clockwise direction. That is different optical behavior. Because both are rotating, this is optically active but rotating the polarized light clockwise. This one is also optically active but rotating the polarized light in anti-clockwise direction. It means different optical behavior. Second meaning, we have again two stereoisomers A and B. A is rotating the polarized light. It means optically active. B is not rotating the polarized light. It is optically inactive. So, one is rotating the polarized light, second is not rotating the polarized light. This is again a different optical behavior. So, here we have different optical behavior in two manner. One in terms of direction, one in terms of direction and one in terms of magnitude. Here we have two different optical behavior. In terms of direction means one is rotating clockwise, suppose plus 10 degree, other is rotating anti-clockwise, suppose minus 10 degree. So, here we have different optical behavior in terms of direction. Here one is rotating the polarized light, suppose 10 degree. Next one is not rotating the polarized light, it means 0 degree. Again, this is a different optical behavior in terms of magnitude. So, the meaning is optical isomers are two stereoisomers show different optical behavior. Two stereoisomers show different optical behavior. They show different behavior either in terms of direction or in terms of magnitude, right? Now, the point is generally we think that optically inactive compound don't show optical isomerism. That is a wrong perception. One active and other its inactive stereoisomers, they both can show different optical behavior. So, the both definitions are just saying this, the one is rotating clock, other is rotating anti-clockwise direction, it means different behavior in terms of direction. Here one is rotating, second is not rotating, that is a different optical behavior in terms of magnitude, right. Now, we need to discuss to be optically active, what the conditions are required, the main point. Optically active means to rotate the polarized light, what the conditions are required. To be optically active, the one and one only important thing is required, that is chirality. To be optically active, compound must be chiral, compound must be unsymmetrical. To be optically active, compound must have a chirality, it means compound must be unsymmetrical, meaning there should be no plane of symmetry, there should be no center of symmetry, there should be no symmetry at all. To be optically active, compound must have one important feature, that compound must be like a chiral, compound must have a chirality, it means compound must have unsymmetry. The meaning is that compound should not have any kind of symmetry, mainly plane of symmetry and center of symmetry. Clear? Two more symmetries are there. axis of symmetry and alternate axis of symmetry. Alternate axis of symmetry should also not be there. Axis of symmetry does not make any sense. AOS has nothing to do with optical activity. The mainly there we have three symmetries that compound should not have: plane of symmetry, center of symmetry, and alternate axis of symmetry, right? The final conclusion is, to be optically active, to rotate the polarized light, compound must have a chirality. Compound must have unsymmetry. It should not have symmetry, plane of symmetry, center of symmetry, and alternate axis of symmetry. Axis of symmetry has nothing to do with optical activity. One more thing, that compound may have chiral center, may not have chiral center. Chiral center is not the mandatory condition. I will discuss what is the meaning of chiral center. I will discuss. The main thing is, to be optically active, that should have a chirality. Chiral center may be there, may not be there. So chiral center is not playing a major role, but the major role is that compound should have a chirality. It should not have any kind of symmetry, plane of symmetry or center of symmetry. First I am discussing what is a chiral center, then I will start discussion what is a plane of symmetry, center of symmetry, and remaining two symmetry, right? First I am discussing chiral center. Now we discuss chiral center. What is a chiral center? Chiral center definition is fixed. Any atom which is sp3 hybridized have 4 different valencies. The small definition for chiral center, any center which is sp3 hybridized and have 4 different valencies. You need to remember only two things, that should be sp3 hybridized and it should have 4 different valencies. That is a chiral center. Any atom can behave as a chiral center if it is sp3 hybridized and have 4 different valencies, right? Example, I will start with example. Suppose I have one acid COOH, CH3, H and OH. This is a lactic acid. This is lactic acid, a very famous example of chiral center. The middle carbon is sp3 hybridized and have 4 different valencies, one H, one carboxylic acid, one OH, one CH3. So this center is a chiral center, right? Second example, COOH, HOH, HOH. This is a tartaric acid. Again the important example of optical isomerism, tartaric acid. In this tartaric acid, if I consider this carbon, here this carbon is sp3 hybridized and have 4 different valencies, one H, one OH, one carboxylic acid, and this is the 4th valency, and the 4th valency is different from rest of the 3, because this is the carbon having HOH and carboxylic acid. So this carbon is a chiral center. See the next carbon. Now focus on this particular carbon only. Here sp3 hybridized, 4 different valencies, one H, one OH, one carboxylic acid, and 4th valency is different. So this tartaric acid is having 2 chiral center, 2 sp3 hybridized carbon with 4 different valencies, right? Now I am just explaining few more example of a chiral center. See, I have this compound Cl and Cl. Check this carbon. This carbon is sp3 hybridized carbon and 4 different valencies, one Cl, second here we have H, third this carbon, and 4th carbon with Cl. So it means that this carbon is having all 4 valencies different. Now check this carbon, one Cl, one H, one this normal carbon, 4th one is carbon with Cl. So this compound is again having 2 chiral centers. 4th example, suppose if I write here Cl, here Br, now check this carbon sp3 hybridized, 4 different valencies, one Cl, one H, one normal carbon, 4th carbon is having Br. Again all 4 valencies different. Here first Br, second hydrogen, third normal carbon, 4th carbon with Cl. This carbon is also having 2 chiral center, right? 5th example, suppose I have this compound like Cl here, and if I place double bond here, now you please check this. This carbon sp3 hybridized, first valency Cl, second H, third normal carbon, fourth double bonded carbon. This is having one chiral center, right? Sixth example, suppose I have this compound Cl and place double bond here. Now you check this carbon, first Cl, second H, third normal carbon, fourth is also normal carbon. If you are feeling that both carbon are same, then try to go for first point of difference. As you move down, you will get double bond carbon, but here you will get a single bond carbon. It means these two valencies are different valencies, right? I am just telling you, if at first sight you are getting same valency, then try to move ahead and try to get the first point of difference. Again you see this example. This carbon, first valency Cl, second H, third normal carbon, fourth is also normal carbon. Here I am getting both carbons same. Then try to get first point of difference. As you move forward, you are getting double bonded carbon, but here you are again getting single bonded carbon. It means these two valencies are different. So carbon is considered as a chiral center. Here we have one chiral center, right? Seventh example. Suppose if I write here Cl, here Cl. Now you check this case. This carbon, first valency Cl, second H, third normal carbon, fourth normal carbon. I got both carbons same. Then move to get the first point of difference. As you move forward, again normal carbon, again normal carbon. Still I am not getting point of difference. As I move again forward, I am meeting at the same point. It means finally I am not getting point of difference. They both meet at the same carbon. It means upper carbon is not a chiral center, and same is the situation with the lower carbon. So there is a zero chiral center. We don't have any chiral center. But if I write the example like Cl here, Cl here, right now we don't have chiral center, right? But if I write one double bond here, now you check this. First valency Cl, second valency H, third normal carbon, fourth double bonded carbon. Chiral center. Here, first Cl, second H, third normal carbon, fourth double bonded carbon. Again, this is chiral center. Here we have two chiral center. So you are getting my point. sp3 hybridized, four valency is different. Suppose two different, and third and fourth you are getting same. Then move forward and try to get point of difference. If you are getting point of difference, that will be chiral center. But after moving, you are meeting at the same point, there is no point of difference, that will not consider as a chiral center, right? Ninth, suppose if I write here Br, Br, Br and Br. Now you check this carbon, first Br, second H, third carbon with Br, fourth normal carbon. So chiral center. This one Br, second H, third normal carbon, fourth carbon with Br. Again chiral center. Here first Br, second H, third normal carbon, fourth carbon with Br. Chiral center, and same here. In this case I am getting four chiral center. So in this way you can check your chiral. Whenever you check a chiral center, simply apply the definition that center should have sp3 carbon or sp3 atom with four different valencies. If you are getting two valencies different, third and fourth suppose the same, then move forward, try to get point of difference. If you are getting point of difference, that will be chiral center. But if you are meeting at the same point, there is no point of difference, it means there is no chiral center, right? So these are the examples of chiral center. Now let's start plane of symmetry. Plane of symmetry. Plane of symmetry means any imaginary plane which bisect the molecule into two equal halves which are mirror image of each other. That imaginary plane is called plane of symmetry. For example, I have this benzene, imaginary plane which bisect the molecule into two equal halves which are mirror image. That is called as a plane of symmetry. This is a horizontal plane of symmetry. Suppose I am writing benzene. If I cut like this, one more possibility, again imaginary plane, bisect the molecule into two equal halves which are mirror image of each other. I am considering it as a vertical plane of symmetry. Next thing, suppose I am writing benzene. Here we have hydrogen anyway. Hydrogen I am considering as a sphere. And now if I imagine one plane which is bisecting these spheres also along with the benzene. So this is called dihedral plane of symmetry. This is called dihedral plane of symmetry. In this symmetry, when I am bisecting the molecule, along with these two hydrogen, two carbons are also bisecting, and I am bisecting the molecule into two equal halves. But in this plane, we are bisecting atoms also. This is a dihedral plane of symmetry. Suppose if I write benzene in this manner, like a 3D view, benzene is like this. Now, if I slice cut, if I like draw one slice cut and cut the benzene into two equal halves, like this is slice cut, then this one is called as molecular plane of symmetry. Here I am considering four categories. Things are same only. We are discussing only plane of symmetry. This one is horizontal plane of symmetry, bisect the molecule into two equal halves, mirror image. Vertical plane of symmetry, mirror image. Dihedral plane of symmetry, mirror images. Here slice cut, benzene molecule, slice cut, that is a molecular plane of symmetry. Once compound is having plane of symmetry, that will never be chiral, that will never be optically active, right? Now I am giving few more examples of a plane of symmetry. Suppose I have this benzene with Br and with Br. Here horizontal plane of symmetry is there, dihedral plane of symmetry is there, and a molecular plane of symmetry, a slice cut is there. Here we have three plane of symmetries. Second example, suppose if you have benzene ring, here Br, here Cl. Horizontal plane of symmetry is not there because in upside we are having Br and downside we have this chlorine. If you go like this dihedral plane of symmetry, both Br and Cl are bisecting, then you will get the mirror images here. So dihedral plane of symmetry is there. And last one is slice cut, molecular plane of symmetry. If I go for a slice cut, again Br and Cl sphere will cut in two equal parts. Again we are getting plane of symmetry. So here horizontal plane of symmetry is not there, but a dihedral and a slice cut both are present. Third one, suppose benzene ring, here we have Br and here we have Cl. This way we don't have any symmetry. Horizontal we don't have any symmetry. This way we also don't have any symmetry. There is no symmetry. This one is not symmetry. This one is, there is no. Only slice cut is there. If I cut in a slice manner, then BrCl both sphere will cut and will get two mirror images. But here we have anyway plane of symmetry. Suppose if I write fourth example, benzene ring, Cl, Cl and Cl, symmetrical trichlorobenzene, dihedral plane of symmetry. Yes, Cl sphere cut in two parts and finally we have two mirror images. One. Second, along with this Cl, dihedral. Third, along with this Cl, dihedral. Three. And fourth one is a slice cut. Slice cut. Here we have a four plane of symmetry. So plane of symmetry means any imaginary plane which bisect the molecule into two equal parts which are mirror image, right? These are few examples. We have, suppose this CH3 Fischer projection I am discussing, HBr and HBr. Here in Fischer projection we have this plane of symmetry bisecting the molecule into two equal halves, and those two halves are mirror image of each other. So this is again achiral because plane of symmetry. Now I am writing here. Now this is again achiral because of plane of symmetry. Sixth example, CH3 HBr, HBr, HBr. Now if you check, here we have plane of symmetry passing through HBr, and after this plane of symmetry we are getting mirror image equal half, which are mirror image of each other. Again we have a plane of symmetry. It means this compound is again achiral, right? It is optically inactive. Seventh case, suppose we have CH3, HBr, BRH, HBr. Here if you check, we have again plane of symmetry passing through BRH. So BRH will come in the plane, they will cut it in the plane of symmetry, and what the remaining part we have, that is mirror image of each other. It means again we have a plane of symmetry. Again this compound is achiral. Eighth example, suppose I have CH3, HBr, but now I am writing CLH and HBr. That doesn't make any sense. You have a CLH, HCl, BRH, because again when I am writing this, drawing this plane of symmetry, they are bisecting in the plane. Remaining part is the mirror image. Again we have plane of symmetry and the molecule is achiral, right? Ninth example, we have this Br and here we have Br, right? Here I can draw plane of symmetry in two manner. One, just dihedral plane of symmetry will get equal parts, mirror image of each other, or you just draw the symmetry and consider these two Br in the plane. So Br will come in the plane, remaining cyclobutyl part in two images, equal images. That compound is having plane of symmetry. Suppose here we have this side Br, this side Br, dihedral plane of symmetry, right? They will cut in that plane of symmetry. I will bisect these two Br and remaining part is the mirror image. Suppose 11th number, I have here I have Br, here I have like Cl. This dihedral plane of symmetry will bisect these two Br and Cl and remaining part is a mirror image. So these are the examples of a plane of symmetry. So meaning is, once you have a plane of symmetry, compound will be achiral, compound will be achiral. Suppose if you have the compound like 1Br wedge, 1Br dash, here we don't have plane of symmetry. If you draw like this, these are not mirror images. A wedge image should be wedge. Here we have a wedge, here we have dash. These are not equal parts. These are not mirror images. So here we don't have plane of symmetry. That part is chiral, right? So once you have plane of symmetry, compound will be achiral. Suppose here we have 1Br, wedge, wedge, wedge and wedge. Plane of symmetry 1, plane of symmetry 2. It means this compound is anyway achiral. Next example, here we have 1Br wedge, this Br wedge, here Br dash, here Br dash. We have plane of symmetry. Again this is achiral, plane of symmetry. Suppose here we have one wedge Br, here we have one wedge Br, here we have a dash Br, here we have a dash Br. Again we have plane of symmetry. This is again achiral. And one more example. Here we have Br wedge, Br wedge, Br dash, Br wedge. Here we don't have any plane of symmetry. That can be chiral. So once you have plane of symmetry, compound will be achiral. Plane of symmetry, this one, achiral. Plane of symmetry, equal images. Plane of symmetry, equal images. Here we don't have plane of symmetry. This molecule is chiral. It means this molecule will be optically active. right? Remaining 3 molecules are optically inactive. So, these all are the examples of plane of symmetry. In next session, we will discuss the center of symmetry, axis of symmetry, and remaining enantiomers, diastomers and meso compounds, right? Thank you.